My name's Alex Thusey, and I'm an ML Specialist Solutions Architect with AWS, based in Singapore and helping customers across Southeast Asia transform their businesses with artificial intelligence and machine learning. In today's session, we'll be talking about feature engineering, the important process of cleaning and preparing raw data into the most useful representations for our ML models to discover patterns and produce accurate results, ultimately maximizing the business value of deployed solutions. First, we'll review exactly what we mean by feature engineering and why it's so important. Then, we'll discuss the tools available on AWS to help, with demos of two new offerings from re:Invent 2020, AWS Glue Data Brew and Amazon SageMaker Data Wrangler. And finally, we'll mention some best practices for fitting feature engineering into your end-to-end machine learning, project management, and workflows. So let's dive in. Whenever we train and deploy a machine learning model, we're essentially representing some real business problem as a maths problem which we can ask a computer to solve. Whether we're predicting a customer's preferences for marketing, classifying documents for process automation, or even building computer vision systems for self-driving cars, underneath it all, our CPUs or GPUs are just working with numbers. And that brings both benefits and problems. While us humans might get forgetful, need to eat, or just make mistakes sometimes, a computer program has near-perfect memory and accuracy and can run billions of calculations per second, 24 hours a day. On the other hand, humans have built-in common sense and a general understanding of the world. If we bring in a new employee and to tell them to do something that's obviously wrong, like grant all loan applications asking for an odd number of dollars, we might reasonably expect them to notice the problem and challenge us, while the computer could happily sit there, running billions of calculations and probably bankrupting us. Since computers don't have this common sense by default like humans do, our ML models will only know the information we give them. So while there's active and interesting research on techniques to embed more knowledge into models, like the paper cited on the slide, this means we need to pay careful attention to how we set up machine learning problems, especially when using more traditional patterns like standard classification or regression tasks, for example with linear or tree-based models like XGBoost. Of course, for most real-world situations, there are lots of different ways we could represent the business problem numerically to our algorithm, and we use the term features to describe these input variables that we choose. Consider the example on the slide. If you were given the task, could you find some reliable rule to predict whether a new dot is blue or red just based on its position? Probably not without some extra information. The distribution seems very noisy, with lots of overlap between the two classes across pretty much all regions. However, what if I was to replot the same data on a different set of axes? Now, it's still not completely clear-cut, but now there's a nice separation that suggests even a simple model could probably achieve good accuracy. Now, if you were a human familiar with the business context that each of these dots represents a customer, knowing what the axes show and what the blue and red classes mean, you might have some extra insights about what could work well and what patterns you'd expect. But assuming our model doesn't have any common sense input, it only sees the data points and the task that it's given. While advanced model architectures can deliver impressive results, well-engineered features give us freedom and flexibility by reducing the complexity that our model has to learn to be successful. Taking the same example as before, the representation on the left will allow even a simple linear model to achieve good performance. We can just classify new points by whether they fall above or below the line. Projecting the same points again onto a different set of axes on the right, this time the points are still clearly separable, but a good decision boundary would be a circle instead. The simple linear model we used before will not be able to find a good solution, even though it's obvious to us humans. Now, of course, we could bring in a more free-form model that's able to discover this pattern, but that model will almost certainly have either more parameters to fit, needing more data points to get the same confidence, or strong assumptions about the structure of the problem, such as only considering circular boundaries that might not always be true. In the real world, we never have infinite data, so we can't just keep making our models more flexible forever. refining our input data is a useful tool for delivering results. Of course, we won't usually know upfront which features are the most predictive either. For example, perhaps we have lots of information available about our customers that might be relevant to the decision. Or maybe we have just a few pieces of information, but lots of possible ways to represent them, like the graphs we saw before. It might be tempting to just throw in lots of data and let the model learn. And again, it's true that a model will, to an extent, be able to learn which features are important or irrelevant for making predictions. But every feature we add is increasing the burden of what the model needs to learn to be successful. If I gave you the complete life story of every customer on the graph before and asked you to decide how to classify them as blue or red, you'd need to consider all sorts of possibilities. Is it about what weekday they were born on, their grades from primary school versus the national average, whether their passport was issued in the same city as they were born? Being confident that you found the right criteria would need a lot of customer examples. Otherwise, it might just be coincidence and would probably take a lot of time. So, although it's true to say that modern machine learning methods can discover complex patterns in data and automatically learn which factors are the most important for a use case, we need to remember that they aren't magic and our data isn't infinite. Manual curation and refinement of the input features could have a really transformational impact on the accuracy you can achieve in practice. Even apart from iteratively refining features to boost model accuracy, we know in general there'll be some more basic integration challenges to connect our source data systems to the model. Considering the many different formats this source data might come in, the likelihood of missing data points, outliers, or incorrect values, and the need to carefully clean and curate the inputs by the time they get to the model, there'll nearly always be at least some kind of transformation required for a real use case. And as a result of all this, data scientists have reported for a long time that the majority of their time is spent on preparing and refining data, not iterating on the algorithms themselves. From this, we can say two things. Firstly, that streamlining this part of the workflow could have significant benefits to the productivity of data science teams. But secondly, that although increasing adoption in machine learning in business is bringing this challenge to more people, it's not fundamentally new to the field. If we'd like to provide new tools to accelerate data preparation, we need to be conscious of the wide range of practitioners out there with different skills, preferred toolsets, and IT architectures. And it's not just data scientist time that these challenges consume either. The ever-growing volume and variety of data generated by today's connected devices and digital processes brings scaling challenges, both for efficiently processing the frequency and size of data produced and integrating the range of different technologies that these architectures grow to depend on. In these optimized environments, even simple data transformation tasks often require hand-coded solutions, distracting engineering focus and producing brittle systems that struggle to adapt to change. This is compounded by the experimental nature of feature engineering. How can we rapidly iterate on these feature pre-processing ideas to optimize model results while respecting the need for stable and efficient data pipelines? And finally, there's the question of how these processes can be governed to protect customer data and system stability while maintaining agility and tracking these experiments to prevent unnecessary rework. So let's look at how AWS helps customers address these challenges and explore our two new visual data preparation tools. Because data may come in many different sources, we should architect solutions considering not just the AI and ML environments like Amazon SageMaker, but also how these data flows will interact with databases, such as Amazon Aurora relational databases and Amazon DynamoDB, or general object storage on Amazon S3, and the portfolio of analytics services on AWS for moving, transforming, analyzing, and managing data. Amazon Simple Storage Service, or S3, is an object storage service that offers industry-leading scalability, data availability, security, and performance, making it the data storage service of choice for building a data lake. For these same reasons, many AWS AI and ML services, including SageMaker, have rich integrations with S3 as a source for training data and a destination for processing outputs. As well as the deeply configurable access management controls S3 offers, customers can use assistive tools like AWS Lake Formation to set up and manage permissions, and Amazon Macie to actively monitor for and protect personally identifiable information. And services like Amazon Athena for serverless querying of data stored in S3 via standard SQL, and AWS Glue for serverless data integration and ETL bridge traditional gaps between what we might call data lakes for unstructured stores and data warehouses for structured data. The result's an ecosystem of services that allows solutions to use the right tool for the right job, but still deliver seamless data movement between tools with unified governance. So considering that these data pipelines may be multi-staged and complex, it's natural that the data scientist won't own the entire path right back to raw data generation. Some transformations may be owned by integration engineers or analyst roles, while others might be created by the data scientists iterating on ML models. These personas have different skill sets and priorities, so forcing them to standardize on one tool might stifle productivity. On the other hand, we know both are facing some similar challenges in authoring pipelines. So to help both types of user accelerate projects, AWS launched 2 new services at reInvent last December, AWS Glue Data Brew and Amazon SageMaker Data Wrangler. Both offer visual interfaces for interactively building and running data preparation sequences, and both offer hundreds of pre-built transform options. But while Glue Data Brew is integrated with AWS Glue, our serverless ETL service, and has particular strengths around scaled data processing and pre-built analytics, SageMaker Data Wrangler is directly integrated into SageMaker Studio, our holistic IDE for machine learning, and has a range of more data science-specific features. In today's demos, we'll show both working together on an example use case. So let's take the path of our data and explore Glue Data Brew first. Now, as we mentioned earlier, AWS Glue offers fully managed serverless ETL for structured and semi-structured data. At a high level, the service consists of 4 main components. Crawlers analyze source data, whether files on S3 or some database connection, to discover and extract the schema and metadata describing its structure. The Glue Data Catalog provides Apache Hive-compatible metastore to store this metadata, whether generated by crawlers or not, including databases and tables which can be associated with access permissions. And when this structure cataloged, serverless ETL jobs can be created and run with a wide variety of data, including batch and streaming jobs with interactive development and auto-generated code. And finally, we can set up workflows combining individual jobs into complex multi-step pipelines, which can be visualized as a graph. Now, AWS Glue supports both Python and Scala, and jobs can use Glue's own dynamic frame component, as well as Apache Spark constructs for distributed data processing too. AWS Glue Data Brew is already generally available in a wide range of AWS regions, including here in Singapore, and brings additional visual data preparation tools to this ecosystem. Users can connect datasets from a range of sources, including the Glue Data Catalog tables, but also direct from objects in Amazon S3, and data from the AWS Data Exchange. You can then run profiling jobs to analyze statistics and correlations over either a sample subset or the entire dataset, and launch visual interactive sessions to explore the data and build transformation recipes without writing any code. These recipes can then be used and reused to run distributed, serverless transformation jobs, including tracking of recipe versions, job executions, and data lineage. Enough slides though, let's see it in action. For our example use case, we'll be analyzing sale prices for residential flats in Singapore, using this public dataset published by the government's Housing Development Board and trying to build a model to predict property values. Here I've downloaded and extracted the source zip file, adjusted the columns slightly so all the CSVs share the same schema, and then uploaded the files to an Amazon S3 bucket. To get started, I'll first open the Data Brew console from the AWS console search bar, and then, from the landing page, open the Datasets tab on the left-hand side. From here, we can create a new dataset connecting these sales CSVs directly from S3, but note the other options available for the Glue data catalog and AWS Data Exchange too. Since the raw data includes an information text file, and sections prior to March 2012 when purchase dates were recorded differently, we'll use the parameterized path option to limit which files we pull through. Selecting our new dataset, we can select to create a project to start building our transformations. We'll pick a relevant project name, check the right dataset selected, and I'll also tweak the default sampling options to help us get a representative sample of the data in our interactive view. Finally, to grant the DataBrew project permission to read our data from S3, we'll assign it an IAM role that's been set up with sufficient access. Creating the project provisions the compute resources to run our interactive session. So this initial startup may take a minute or so, and we should note that the infrastructure is billable for the time that we're using it. Once it loads, we'll see the main grid view of our project, showing our sampled subset as a data frame with some additional statistics at the top of each column. Of course, it's really important to remember that this is only a sample, so the statistics here may not exactly match the full dataset. We'll use the transforms from the toolbar to edit our dataset and see the live preview as we go. Each transformation we apply will be added as a step to the recipe over on the right-hand side, which we can navigate and edit. And when we're ready, we can either click the Create Job button at the top to run our working recipe on the full dataset and output to S3, or publish the recipe as a new version for running on demand or on a schedule outside of this project view. As we can see in the grid, each record describes a sale with 11 columns, including information about the sale date, the property itself, and finally the price. Although these sample statistics are useful, we can also open the Profile tab and create a new profiling job to analyze the entire dataset. I'll select to save the JSON results to our same S3 bucket, but a separate folder to keep things tidy. And since our data is small, we can limit down the compute resources to be used for the job. Finally, we'll use the same IAM role as before to grant access. While the job runs, we'll head back to the grid view and start building our recipe. First, let's take the text values of our flat type field and map them to a numeric sequence. Since it's pretty clear there's an ordinal relationship here that's likely to correlate with price to some extent. Now, the exact hierarchy of the top two options, executive and multi-generation, is probably debatable, but we'll be building tree-based models, so hopefully that shouldn't be too big of a problem. Likewise, for story range, the ranges seem to be regularly spaced, so taking just the starting floor should be enough to represent the impact to our model. There are a few different ways we could go about this, but I'll use a simple regular expression to extract the first number and then convert that result column to a numeric type. The remaining lease column includes several different formats. So DataBrew has inferred a string type, and expanding out the list of unique values, we can see some records specify months, whereas others give only the years. We can use another regular expression to split the column after the first number, since this is always the years. And again, once that's done, we'll convert the first text result to a numeric type and give it a clearer column name. While we could also try to extract the months component where it's available for extra precision, if we open the now completed profile job and check the column summary section, we can see that even the years are already missing for a significant proportion of our records. So the fraction with month data will be even smaller. Adding in the extra precision could introduce bias to how our model considers the examples where we don't know it. So in this case, we'll go ahead and drop the extra field instead for now. Finally, let's revisit our address fields, street name and block. Rather than trying to use this data directly for modeling, we'll use the join transform to link an additional addresses dataset I prepared earlier. Here, we've used the public OneMap Singapore API and a SageMaker processing job to create a lookup table from street address to location coordinates. Clicking through, we'll select to left join it to our sales data and specify our two lookup keys, block and street name. We'll deselect these extra columns from the result as we don't need to duplicate them, and then go ahead and click Finish. Now there are plenty more refinement steps we could take here in Data Brew, like one-hot encoding our remaining categorical fields or logarithmically scaling some of our numerics. But this feels like a good point to draw the line between data engineering and data science. So let's now publish our recipe version with a short description. Finally, we'll open the Jobs tab and run a new job against our sales dataset. We'll give our job a name and use the recipe we've just created. Saving the results to a new folder in S3. Again, we'll reduce the number of processing nodes since our data is small and use the same S3 access permissions as before. The job will then run and store our transformed data in S3. So while we wait, let's introduce SageMaker Data Wrangler. Now, although AWS Glue is great for accelerating our ETL pipeline build, many data scientists are looking for even easier options to use both pre-built transformations and dive into custom code when needed. While accelerating the feature extraction itself is one important issue, there are also some other more ML-specific, MLOps-style challenges to consider for our end-to-end projects. Since most organizations will have multiple ML projects in their portfolio, we'd like to take steps to avoid rework and redundant feature pipelines where possible. And to help foster reuse without slowing down innovation, mechanisms for searching and discovering pre-built features with appropriate governance will be really useful. For machine learning in particular, we also need to be especially sensitive to any possible biases or skew introduced by the data preparation pipeline, which could subtly impact deployed model performance or lead to unpredictable results. Now, Amazon SageMaker is our fully managed service to support the end-to-end machine learning lifecycle, all the way from data collection, preparation, and annotation, through building and tuning models to deploying models and their ongoing management and monitoring in production. As you might expect from that scope, it's a broad service with a lot of different integrated features and capabilities. And for data preparation in particular, this includes SageMaker Ground Truth, supporting human data annotation with pre-built and customizable user interfaces, SageMaker Processing for serverless general data processing jobs closely integrated with the SageMaker experience, SageMaker Feature Store for managing and sharing created features, SageMaker Clarify for detecting bias and interpreting model predictions, and of course, SageMaker Data Wrangler. We'll access Data Wrangler through the SageMaker Studio, our integrated development environment for machine learning. Data Wrangler itself will provide us tools to select data from multiple sources, easily compose different built-in transformations, and deploy data preparation workflows, conceptually similar to Glue Data Brew at a high level. But with Data Wrangler, we also have some more data science-oriented capabilities, including writing custom transformation steps in simple pandas where needed, building custom visualizations to explore specific features, running pre-built analyses with SageMaker Clarify to check for potential bias problems in the dataset, and even creating quick models to fit a basic model on the dataset and get an initial idea of feature importance rather than relying on correlations alone. Now, let's see how it looks in practice. So our Data Brew recipe job from earlier is now complete, and we can actually register its output folder as another Data Brew dataset, as I've done here, to use the profiling functionality to check our results. The correlation matrix is a little more interesting now that we've extracted some extra numeric fields, and we can see that, for example, our flat type index is strongly linked to the total floor area, and that properties further north at higher latitudes tend to fetch lower prices. Over in the next tab, I have my SageMaker Studio environment open already, and you can check out the SageMaker Developer Guide for more details on how to onboard to Studio if you're not already familiar. We can access Data Wrangler either by creating a new flow from the launcher screen or opening an existing data flow file. Like in Data Brew, this interactive environment will spin up some compute infrastructure that we can see and manage over in the Resources tab. To get started, we'll select Amazon S3 and use the browser UI to select the output CSV file from our Data Brew recipe, finally giving the dataset a name to appear in our SageMaker data flow. This automatically generates two nodes on our data flow view, which Data Wrangler uses to represent the pipeline we're building. The first node is the source itself, and the second is the inferred data types, which we can review and customize if needed. Before we dive into transformations, we can first create some initial analyses of our data using up to the first 100,000 rows to guide us. For example, we can choose to create fully custom charts of the data with code using pandas and Altair, or use the UI options for common charts like histograms, or a scatter plot to show, say, the relationship between floor area, resale price, and flat type. We can also make use of the more advanced pre-built analyses for machine learning, including detailed bias reporting with SageMaker Clarify for investigating whether subgroups in our input data may be poorly represented in ways that could introduce unwanted model bias. One particularly useful tool which I'll use first is the quick model analysis, which performs a basic train-test split of the data, fits a random forest model, and then reports the test set accuracy and the measured feature importances of each input field. While simple correlation metrics can still be a good guide for finding highly predictive features, going beyond this to actually train a basic but nonlinear model and measure its accuracy and fitted feature importances can really take our insights to the next level. In this case, the quick model found an MSE of around 3.5 billion, equivalent to a root mean squared error of about $60,000, which seems like a pretty fair starting point. It suggested that floor area and nearest town are probably useful predictive features, while our raw transaction month and block number weren't that helpful. Heading back to our flow view, let's finish off transforming our dataset. As in Data Brew, these different categories offer hundreds of pre-built transforms with no code required. For example, we can split our month text fields on a delimiter, just like we did for other fields earlier. But here in Data Wrangler, scientists have a bit of extra flexibility for more custom, complex transformations. For example, we can write composite expressions directly in Spark SQL and make use of vectorized columns like this month split to represent more sophisticated featureization functions in a single step, rather than needing to compose several steps through the UI. With the custom transform option, we can also write complex data frame level transformations using our choice of either SQL, PySpark, or good old pandas and NumPy. For instance, I can paste in some code to calculate the straight line distance from each flat to the city center. In this second flow file I prepared earlier, we've added a range of other steps to help show what a more complete flow might look like. For example, joining in additional data sources, in this case a list of rail stations to find the nearest one, and branching out the flow to serve potentially separate use cases. Once we're happy we've prepared and curated the field for our mathematical model to be successful, perhaps adding extra analysis charts and diagnostic branches to check, we're ready to export our results. Heading over to the Export tab, we'll select which node of our graph we want to output, and then choose how to use it. This could be directly as Python code, or a pre-built notebook guiding you through the commands to run the job, either directly as a Data Wrangler job in SageMaker processing, as part of a SageMaker feature pipeline, or with extra steps to load the results into SageMaker Feature Store. I ran this example earlier already, So if we head over to our SageMaker Components tab and select the Feature Store section, we can see our one registered feature group. We can search this list by a range of fields and drill into feature groups to explore their columns, as well as sample queries for building views. So with Data Wrangler, we have our choice to export our work to Python, run a processing job to realize the results in S3, or integrate with SageMaker's own CI/CD and feature management tooling. Now, hopefully those demos help to showcase some of the similarities and differences between the two tools, and how both can be useful in preparing data for machine learning. Before we wrap up, let's take a step back and review the bigger picture of how these and other tools work together to accelerate our ML workflow. Maybe the first thing to mention is that, especially in the context of bigger teams with multiple projects, building the features is only part of the story. With Amazon SageMaker Feature Store, we can register groups of features, including descriptions, in a searchable store to help manage our engineered features and foster reuse. Data can be ingested both by streaming or in batch, and each feature group can be configured for offline batch retrieval, for example, for use in model training, online low-latency querying for responsive real-time inference, or both, with the feature store ensuring consistency. As well as the service APIs and the high-level SageMaker Python SDK support, data scientists can explore registered features and groups directly through the Studio UI. And batch-enabled feature groups can also be configured to create Glue data catalog tables, closing the loop back round again to AWS Glue. So for many real-world applications, the pipeline from raw data collection to advanced AI model is non-trivial, and it's likely to be a shared responsibility between teams with different skill sets to ensure the business can deliver both robust data pipelines and high-performing models. With Amazon S3, AWS Glue, and Amazon SageMaker, AWS customers have a flexible and integrated set of tools to help these different roles collaborate under fine-grained access controls. And although they're optimized for different users' needs, the intuitive visual UIs offered by Glue Data Brew and SageMaker Data Wrangler can accelerate communication, helping data scientists build more efficient and scalable transforms directly as they experiment, and accelerating the pace of iteration that can be delivered closer to the raw data ingestion too. As well as custom modeling on SageMaker, a wide variety of other AWS AI services can build models from this data with no machine learning expertise required, such as Amazon Recognition custom labels for computer vision, Amazon Comprehend for text understanding, Amazon Forecast for time series forecasting, and many more. If you'd like to read more around these topics, the AWS MLOps white paper discusses feature engineering in the context of the broader machine learning project management and automation. For anybody looking to dive deeper on data brew integration and automation, there's a recent post on the AWS Big Data blog with a step-by-step guide showing how you can orchestrate data brew jobs with AWS step functions and build data dashboards. And for any data scientists who are bored with traditional methods, I think there's some really exciting research going on recently into how self-supervised pre-training and attentive neural networks could raise the bar for how tabular models deal with missing values and correlated features. Definitely check out this Tab Transformer paper by researchers from AWS and Postera. Finally, you can of course find detailed documentation and examples from the developer guides for both Glue Data Brew and SageMaker Data Wrangler. AWS Training and Certification offers many free and on-demand digital courses, as well as virtual instructor-led training with AWS experts to help you continue your learning journey. Do check out the aws.training website and our ramp-up guide with suggested options for getting started and also working towards certification exams to validate your skills with industry-recognized credentials. In particular, you can visit aws.training/analytics or aws.training/machine learning, depending on your focus. Thanks very much for joining today's session. I've been Alex Thuzy, and I hope you've enjoyed our quick overview of feature engineering with AWS. Please do fill out the session survey, and I look forward to connecting with you again next time. Until then, happy featureizing.